When millions of pounds of concrete and steel slide into the ocean, the collapse is immediate. When physical forces exceed structural integrity, failure is catastrophic. This was the reality for the Sleipner A platform, a massive reinforced concrete structure designed for offshore oil drilling. Its sudden structural failure upon submersion resulted in millions of dollars in commercial losses and severe timeline setbacks for the entire operation. Investigators initially suspected a physical defect in the construction materials, assuming the concrete itself or the detailing of the internal rebar was inherently flawed. The actual cause was entirely computational. The physical structure was built using an extremely coarse finite element analysis, or FEA model, that underpredicted the shear stress resultants at a critical section by about 50%. The software model relied on a single lower-order element, capable only of calculating uniform stress variations. This completely missed the actual parabolic variation of shear stress across the physical concrete. Trusting standard computational modeling tools without stringent mathematical verification can mask fatal design weaknesses, leaving them hidden until the exact moment real-world physics takes over. The tool used in the vast majority of commercial FEA systems today is the conforming finite element, or CFE method. It relies on a force-driven mathematical approach. CFE models possessed a specific mathematical vulnerability. When a simulation is undermeshed, meaning it uses large, coarse geometric elements, the algorithm artificially stiffens the simulated structure. This artificial stiffness leads the software to overpredict the structure's actual load-bearing strength. Because of how the equations resolve, a CFE model will always approach the true physical limit of failure from the unsafe side of the calculation. There is a corrective mathematical framework to this problem, known as equilibrium finite elements, or EFE. EFE differs from standard models by strictly enforcing static admissibility. It guarantees the absolute equilibrium of tractions at every single element interface across the mesh. By inverting the mathematical approach, EFE ensures a structure's predicted strength is a safe certainty, regardless of how coarse the mesh is. To verify the accuracy of a finite element code, engineers run theoretical limit pressures against known exact mathematical solutions to ensure the software matches reality. This chart compares limit pressures against the exact analytical solution at 1.00. The top CFE curve dangerously overestimates physical strength with a coarse mesh, converging downward toward reality only as the mesh is refined. The bottom EFE curve begins as a safe underestimate, steadily climbing upward toward the exact limit as elements are added. The gap between these curves defines algorithmic uncertainty, the exact margin of computational risk. The FEF curve remains entirely in the safe zone because its calculations are governed by the lower bound theorem of plasticity. This mathematical rule ensures that predicted strength will never exceed actual physical capacity. Because of this theorem, an engineer running an FEF model with just a single crude geometric element will still receive a mathematically safe load prediction. Applying the lower bound theorem ensures that any lack of computational refinement defaults to a harmlessly over-engineered physical design, precluding structural collapse. If FEF provides a mathematically safer baseline, there has to be a reason commercial FEA systems historically abandoned it in favor of the riskier CFE method. The historical limitation of FEF was a mathematical anomaly known as spurious kinematic modes, or SKMs. An SKM is a zero-energy pseudo-mechanism. It occurs when the mathematical model creates a false mode of edge displacement, suggesting a part of the structure is moving without any actual force being applied. When these false displacement modes appear, they create singularities within the assembled stiffness equations, ultimately crashing the simulation. To solve this, researchers developed a geometric solution by assembling a larger macro element from a group of triangular primitives. By forming a quadrilateral, any SKMs are trapped entirely on the internal edges, where the triangles meet. Because the SKMs cannot propagate to the exterior edges of the square, the external boundaries of the structure remain perfectly stable for matrix calculations. Containing these pseudo-mechanisms internally stabilize the EFE formulation, rendering it robust enough to process complex, large-scale structural models. Analyzing static structural weight is only one part of mechanical engineering. Components like energy storage systems and turbomachinery present more dynamic challenges. Engineers have to separate simple external boundary forces, like physical contact or weight, from internal body loads that originate from the material itself. These volatile body loads include volumetric thermal expansion from extreme heat and mechanical inertia generated inside rapidly rotating disks. This diagram illustrates how the FEFE macroelement accommodates internal body forces. It translates the internal thermal and mechanical loads into equivalent tractions directly mapped along the outer boundaries. Because the internal edges carry the body force, the resulting stiffness equations generate a singular matrix. Under normal circumstances, this matrix cannot be inverted to solve the equation. To compute the result without crashing, the software replaces the standard matrix inverse with a pseudo-inverse, generated using singular value decomposition. Isolating these body loads mathematically allows EFE to accurately simulate high-energy, volatile physical states without destroying the foundational stiffness equations of the model. The value of this mathematical stability becomes apparent when examining tangible structural feedback, such as the internal stress fields of a tapered concrete cantilever. This image displays EFE principal stress trajectories. Even with a coarse mesh, it maps clear compressive load paths. Tensile trajectories offer a visible readout of internal physics. Engineers use these legible lines to design specific reinforcement layouts, like this strut and tie model. Extracting this level of reliable load path visualization from standard CFE models requires massive mesh refinement, costing significant computational time and processing power. Generating accurate, continuous polynomial stress fields directly connects abstract computational mathematics to practical, load-bearing construction decisions on the ground. Mechanical engineers routinely design high-stakes industrial components, like heavy-duty pressure vessels, that hold immense volumes of stored energy. When structural failure guarantees an instantaneous and lethal release of that energy, relying exclusively on an algorithm that structurally over-predicts strength is an unacceptable engineering risk. The path forward does not require discarding CFE, but rather integrating EFE as a strict dual solution, allowing engineers to calculate the exact, proven bounds of safety from both extremes. The necessity of calculating practical mathematical bounds on physical objects is an engineering discipline dating back to Archimedes of Syracuse in the 3rd century BC. If you enjoyed this video, please give a like and subscribe. Today's video was brought to you by Synestec Systems LLC and founder Shane Persinger. True engineering mastery requires knowing the physical materials and perfectly bounding the mathematical limits of the tools used to test them.